Hey, what's going on, everybody? You know who it is. It's your boy Algebra, featuring Algebra Baby in the background. My man Averick laying here in my lap while we talk to you about linear approximation. This is his first introduction to calculus, so I'm hoping that he just picks it up and is able to run with it, and he can just start taking class with you guys when we get back. Probably not. So we might as well go ahead and get started. Let's go. All right, so the basic idea of a linear approximation is that if I gave you a curve in the beginning, right, and this curve, you have made a tangent line for it, we would say that this tangent line is good for um, kind of developing your sense of what it means to have the very next step, that instantaneous rate of change. But I want you to start to think about this tangent line as potentially being an estimator. If we use the tangent line as an estimator for this actual function, it's not really a good estimator once we get here. But if I wanted to estimate the value of lines that are really close to that value that we started off with, we can see that it's a much better estimator for what the actual value is on your function the closer you are to that point. Like, it's great when you're in the middle lines. It's okay once you get farther out, but eventually it becomes just a bad idea. So the closer we are to this point here in the middle, the better. If I can zoom all the way down in there, for a period of time, you can't even really tell the difference between the tangent line and the actual function. That's what we want to try to do, is we want to try to use our tangent lines to estimate the actual value for some potentially really ugly numbers that we might have come up with. A linear approximation has two pieces involved in it. One is that you have to know what that actual point is. This actual point absolutely matters when we're talking about a linear approximation, because you have a point, and then we're using that derivative idea to come up with a slope. AKA, we're creating point slope form. We're just finding the tangent line at a particular point. This linear approximation idea is going to be used to estimate a particular value that may come out to be something that's, bless you, is going to help you estimate a particular value that your calculator is the only way that you would get it otherwise. Let's go ahead and do an example. The example I want to give you is a basic square root function. Y equals, and we'll go square root of x minus 2. So what do you know about this? You know that this is 2 comma 0. It doesn't extend in the other direction. A whole lot of information. But the number that I want to ask you about using an actual linear approximation in this is, I want to know what you would get for f of, let's go with the 27.1. You'll see why I chose this 27 pretty quickly, because if you just plug in your 27, then you would get 25, and that's a really comfortable number. But the fact that I put in 27.1 really starts to distort the picture just a little bit. Is it 5.0007? Is it 5.021? Like, I don't really know. And because I don't really know, I need a way to approximate this value. Hopefully that's starting to make a little bit of sense. I'm not giving you an exact value. I'm going to be able to approximate it. And I'm going to be able to approximate it by looking at the tangent line, which runs through 5, or excuse me, 27 comma 5. If I use my 27 comma 5, it's going to generate that line that's really, really, really close. And I would consider 27.1 really, really, really close to 27. It's not exactly there, but it's close enough that we can use it for an approximation. How? Well, first things first, I found out that it was 27 comma 5. I chose 27 because it was close and convenient. The 5, that is the actual value I get for f of 27. And since all I'm trying to do is figure out the f of 27.1, I'm just going to be doing that same process. Now again, I get it. You could just leave it as a radical, but if I need to turn it into a decimal, now what? I have to be able to do this linear approximation idea. It's more of a conceptual understanding because with a calculator, you just plug it in. Without a calculator, can you really get me close? That's the question. So I chose 27 because it was convenient. I plugged it in, so now I have an actual point. The next step is I need to identify slope. And the slope comes from the derivative. Way back in the day, you learned how to deal with the square root for dy dx. Dy dx in this particular instance is 1/2 times x minus 2 to the negative 1/2. Remember, that's because I changed it from a radical into an exponent. I took that exponent, moved it down to the front, reduced it by 1. I did the chain rule on this, which was just a 1. And so I ended up with that really complicated looking thing. I'm going to rewrite it this time with the radical. From here, plug in your value. The slope at x equals 27, you really have to go and plug that 27 in, is 1/10. Okay, so what this has all led me to is having a linear approximation that is resembling that blue line. It would be y equals the linear approximation y. So I'm actually going to change it from being equals to this approximation symbol. 1/10 x minus 27 plus 5. All of this leads me to being able to say that if I want to approximate the value at 27.1, all I have to do is plug it into this. I don't actually have to worry about doing a radical that involved this decimal as well. I can plug it into this linear function, and it's going to give me something like 5.001. That's a lot. 5.010. So I would consider it a pretty good estimator when we're talking about 27.1. Would I plug in 28 into this? Maybe. It's starting to get a little bit hairy there, starting to get a little bit fuzzy. But I definitely wouldn't want to plug in a number like 146. That wouldn't make any sense at all. So what I want to use this linear approximation function for is to estimate values that are really, really, really close, like 27.1, like 26.9. The farther away I get from 27, the less useful it will become. So one of the secondary uses for this linear approximation idea, and I'm going to redraw my picture while I talk. A secondary use for this is to talk about margins of error. Like, when does it stop actually being a good decision to use this approximation? Well, some people would say that um, it's only a good approximation if you're within 1/100th of the actual value. So how would we deal with that? Well, what we would do is we would take our original tangent line that we created and set some boundaries for it, like that red line and this green line that are below it. These two values are saying this is a margin of space that I'm willing to use this approximation within. If the value actually is beyond this plane, this area, then it's not a good estimator anymore. And so one of the questions that I'm going to ask you is, can you identify these boundaries? Well, yes, you can. We can absolutely identify these boundaries. What we would be saying is something to the effect of the linear approximation needs to be, I'm going to use the letter L for it. The linear approximation of L minus the actual value needs to be less than, we said 100th. If we can solve this inequality, which is actually an AND problem, which is giving us a top and a bottom boundary, we can figure that out. We're actually creating a set of boundaries that says this is when it's actually really, really good to use this function as an estimator. So trying to use this function as an estimator, I can't actually do that by hand. I have to use a calculator for it, and that's completely okay. Here's what I would actually plug into my calculator. I would plug in the y value the first time is just my linear approximation. I'm also going to plug in the original function. But with that original function of x minus 2 underneath the square root, I'm going to add the 1/100th to it. Taking that information, second, calculate. I want the intersection between those two lines. What that's going to tell me is it's going to tell me, hey, here's the boundaries for which you are able to estimate effectively. And I'll tell you what, we thought it was a great estimator. We thought for sure we had created something that was going to be useful at 27.1, but I found out that my values are like 2/10 off. It's not actually a good estimator when I plug in my points. The points that I get are the points of intersection for those two curves ended up being at 30 and 23.9. Those essentially are telling me that anything within those two boundaries is going to be a pretty decent estimation if I just use my linear approximation function instead. And that's a pretty cool idea, is that you can get close enough using a linear function if you've zoomed your graph all the way in. I wish I had the ability to just screen capture what I was able to do on my calculator in solving that, but my license expired, so I don't have that capability right now. On Monday, I intend to show you all this information again. I also intend to go over a lot of the things that I ask you to review throughout the week. All right, so your homework regarding linear approximations is going to be in the book. It is on page 255. You're looking at numbers 1, 3, 11, 17, 18, 21, and 24. Good luck. Peace.